The file system part of an operating system, some authors will consider the file system separate, a separate system that talks to the operating system, but many will also just consider the file system as part of the operating system. Okay, so start off, and this is going to be kind of boring at the beginning at least, because it's just, you know, slides and definitions, but file system, and sometimes the file system is basically a way of organizing the data that's being used on the computer, and we want to organize the data in such a way that, depending on what our application is, we can either write to the disk drives or read from the disk drives quickly, or do both. It really depends on what our application is. So there's usually a tight coupling between the operating system and the file system, and sometimes even the file system is considered part of the operating system. Okay, so files, the point of the files is, like when we talked earlier in the course about processors and reading and writing from memory, memory runs on electricity, and the idea is that once we have the option to shut our computer off, we can shut the computer off, and we'd like to still be able to record our files. So we need to record our files on some kind of a medium that doesn't need to have electricity running to keep it in memory. So different types of mediums to record disk on that don't require that electricity to always be running would be hard drives, floppy disks. I'm almost getting to the point where I need to take floppy disks out of the slides now. Optical disks, which are basically like DVDs and CDs. So those are basically disks where you record the data, and then the way you retrieve the data off the disk is actually to bounce a light off of it. So it gets a reflection, and then you could read the data off of it. So there's no wear and tear on the disk, unless you scratch the disk. And then flash memory is kind of like those memory things you plug into your computer and copy files onto, and then pull them out of your computer. So when you plug those into your when you plug those into a computer, the operating system detects a new piece of hardware that's been added, and then will add it to its file system. It detects that it's carrying files on it. And then the other thing, if your computer is connected to, let's say, the internet, you can have a file system on another machine as long as it's connected to the internet. So connecting to a file system that's not even physically on the computer your operating system's running on is still allowed. Okay, so now to get at a file, so the file's going to be stuff that you save. It could be Excel, if it's a Windows operating system, it could be Excel spreadsheets, your resume in a Word document. Different types of files that are going to be on the system. You're going to have to go through the operating system to get to the file you want. So the files are going to have names. And the file will, the name will be used for the file system to then be able to go out to find its location. Then there'll be utilities on the operating system that can interact with that file name. You could change the file name if you want to. And the file names could also have prefixes or suffixes, which may or may not, depending on the operating system, give meaning to the files. So you probably know, and we'll talk about individual operating systems like Linux and Windows down the road, but you probably have seen files that have, like a Word document might have a name, and then it'll be .doc or docx. And that name doesn't actually give it a different meaning unless the operating system decides it wants to have a different meaning. So for example, a doc or docx file would be, if you went to click on it, the operating system might read its name and see that it ends in .docx and assume the file is input for a Word program. So in that case, if you double click in Windows, if you double click on a doc or docx file, the operating system will kick off the Word program, then open up your file and feed your file as input into the Word program. So it'll appear like a Word document. Okay. And then for organization, a lot of operating systems do this, but you don't have to do this. But you could put your files, instead of them all being in one place, you could organize them in a hierarchical way using what Unix-based systems typically refer to as directories and Windows systems refer to as folders. But you can have your file system have a tree of folders or directories, and then inside those directories we have the files. Okay. Then somehow, and this depends on how you want to run the operating system wants to do this. There is no right answer for doing this. But we'd like to keep data about the files. And data about the files could be like who is the owner of it, who is the creator of it, who was the last, well, when was the last time the file was touched, like when it was created, when it was most recently modified. So somehow, besides the data that's in the file, we have to somehow reserve some space for that information too. So sometimes that's referred to as metadata, which is kind of like data about the data. And we can also keep track of how big the file is, and pretty much any other data you want to keep on the file. So that will make the file size grow a little bit, and also making updates to the file would have to now not only update the files, but update the metadata about the file. So the file system, and like we said, that's part of the operating system, includes utilities, how to initialize those parameters, change those parameters, remove those parameters. Directory utilities are for renaming and deleting directories and altering metadata about the files. Utilities for like copying files, moving their location within the file system. That also ends up being part of our file system. And we also want to keep track of free space. Okay, then another thing we want to, we may want to have, depends on our operating system, is permission to access the files. So the files could have owners to them, and then if you go to access them, the operating system will check who you are, and if you have the permission to access the file. You might be able to read the file but not write to the file, and someone else or someone who's in a different group, if they start grouping them together like Unix-based systems, people in that group can read and write the files, but people outside of that group might only be able to read it, or could have permission that says nobody's allowed to read it other than the creator of it. So the most important purpose of the file system is to manage the user's data, including storing and retrieving and updating data. When the main memory, or cache memory, whatever, wants to send data to the file system, it could send it in a number of ways, but the most common way is just a stream of electronic bits going to the file system, and then the file system would have to save this file. Either save it in a brand new place on the disk, or save it on the storage where it currently is, on the secondary storage. So one of the most common ways to store files is on what we're going to call a disk. And what we basically mean by a disk is some type of medium that is circular and has tracks on it. I mean, we could store disks on something that is linear, but then if we ever wanted to load those into a device that can read it, it would have to be like a really long device. So most files use the concept of a disk. So a disk is basically for space reasons. The information is circular and goes either from the inside out or from the outside in. And then, like we were saying earlier, a network file system, we could connect, just because our operating system is on, let's say, our current machine, it doesn't mean that the file system we're talking to has to be physically connected to that machine. We could go through the network, but then, like we were talking earlier about permissions for files, that would still have to be enforced even though you're going through a network. out to a network file system. So really, our operating system, as long as it has the ability to communicate to a file system, doesn't have to be physically on the machine we're currently looking at. Okay, so taking the idea of what we said earlier was a disk. We would have a disk, which could be like DVDs you've used, or CDs, or even if you have seen those floppy disks that have the opening in the middle so you can have a read and write head, look at it. What generally happens is the operating system, or the file system, part of the operating system, will break down each of the tracks. We'll call these tracks, areas that we can write data to. We'll break down the disk into tracks, and then, since a lot of data these days can be put on one particular track, and maybe we'll have files that are so big they might even be able to fit on a quarter of a track or an eighth of a track. What we'll do is we'll cut the tracks into equal length pieces called sectors. So it's just some, things to get used to. Track is one loop on the disk, and then we could cut that up into many sectors if we wanted to, each track. And what we now want to do is store our files somewhere on the disk. So, any suggestions how, let's say this was our disk and it was completely empty and a new file was coming in. And let's say we decided, like, here's the beginning. And we'll write from the outer track to the inner track. And if a new file came in and it needed to take up, let's say it was 3.5 sectors long. Right, so the file is out in main memory. How big it is doesn't really correspond to how big of the disk we choose, or how many sectors, or how big a sector is. That's just something the file system has defined. This is just a file coming in that we need to write. So where would be a good place to write it? Let's say this is a brand new disk, it's completely empty. That would be a good place to write an incoming file that's maybe 3.5 sectors long. Any suggestion? Start at the first sector and just write it here, and then here, and then the third one here, and then maybe up to about half of the sector and just stop here. Right? I mean, since the disk is empty, we might as well do that. But now if we came to this disk looking for that file, and we said, okay, here's the file's name, where is it? How could we know where it is? Would we just assume it's the first file, or? And we have to somehow think of a way to say, this file, I want this file name, where is it? And we just started writing it here, so. Yeah?
Reserve one sector for file pointers.
Okay, so, and like we say, in operating systems, there's really no right answer to every question, but there's a few answers, and some might be better than others depending on how we want to look at the problem. But maybe what we'll do is we'll take maybe the first sector. Like I say, this is we'll use the computer science nomenclature of starting with the number 0. So we'll consider the outer ring, the outer track as track 0, track 1, track 2. And then starting like at 12 o'clock, we'll say that this is sector 0, 1, 2, and 3. So maybe what we'll do is we'll dedicate one sector to being the index. What did you say? A collection of pointers? Okay, so something like this file name is at that location. So we have some data here that just says where the files are. So we'll say that, and let's say one file is the green file. So if we wanted to allocate contiguous files, meaning once we start writing it to the disk, it should appear on the disk in a row. Let's say we wanted that. And there might be an advantage to that, and then there might be a situation where that's not really needed. So what we might do, we might let one sector be the index for where everything is on the disk. And then maybe this, starting with the very next sector, the green file starts and goes around to here, and that's not enough room. This sector was not enough room for the file, so we went into the very next sector, which is going along here. That's not enough, so we kept going along here. Now we've covered the entire outer track, so we just go in one more and keep going. The file goes to here, and it's still big enough that it needs to go to here. And it might not go to the very end. There might actually be some wasted space here. If we decided that we don't want the next file coming into our system to overlap on a sector basis. So then let's say another file, which I'm calling the yellow file. The yellow file starts on this sector and just keeps going. Like I say, if our operating system decided to read and write files on disk in contiguous form, meaning once you start writing it, every record after it has to be right after it on the disk. If we did that, then this sector and maybe this sector, and now we're coming into the next track, and this sector would be another file. So this is actually considered contiguous because the read-write arm goes around and then moves in one and then keeps going and moves in one and keeps going. So now we might have a sector here that's empty. Maybe there was a small file here and then someone deleted the file, so this went back to being empty. And let's say these two sectors are a blue file. So the idea of putting things in contiguously means if a user comes along and deletes a file, we may have spots on the disk, or sectors on the disk that are unused. So also in our index of where files are, we probably also want to keep some pointers to where sectors are that are not being used. So now if a new file needed to come in, and we happen to know we have one contiguous sector in a row and the new file coming in could fit in there, we could put it in there. If it doesn't fit in there, we may have to find a place with two contiguous sectors in a row. So now the question is this: do we have to, what is an advantage and maybe what is a disadvantage in imposing on our file system that the files be recorded contiguously? What would be good about that? Having our files appear on the disk in a row. Yeah?
You figure out exactly where a pointer was in that file, just a simple map.
Well,
Like if you know the size of a sector, you can, it's like a page calculation, you know exactly where it's.
well, but let's say all the sectors are the same size. And I know it seems a little weird. You'd think like the inner circle, as you get closer to the inside, it's kind of like a pizza pie. Like the closer you get to the middle, the smaller the pie is. So you might think like this sector has less data than this sector. But let's just say all sectors are the same size. So, and let's say we decided we want the files to be located contiguously. So let's say it's a Word document, it's like your resume, it's 2 pages long. And when you save it, it gets saved in an order, because there's order to your file. And we decided to put your resume across 2 sectors in a row. We could have put like one sector here and then another sector over here if we wanted to, but that's going to add some more overhead, but there might be disadvantages and advantages to doing contiguously and not contiguously. So what's an advantage of doing it contiguously? Whether it's on the disk and everything's in a row. Like if you went out to grab the file, the entire file, there'd be less work. Because once you know where it begins, once you go to the index and know, oh, it begins here, the operation of getting the file is pretty quickly. We just get this one, we know we're at the spot where the next segment starts. So we can just grab it quicker that way. So that would be an advantage to like bringing in the whole file. Is there an advantage to saying, I'm not going to require that the file be all sequential, I shouldn't say contiguous on the disk? Is there an advantage to not doing that?
Use your disk space more efficiently?
Yeah. But what's the, right, so what's the trade-off?
It's slower.
It's slower. So it would end up being, and like I say, with an operating system, there's no right answer. There's just some answers are better than others, depending on your application. So suppose here, we decided we're using the sector method of basically taking the tracks on the disk, and then the operating system comes along and divides them into sectors. So I have the same idea that, let's say this red sector is the index to where everything starts. And now I'm saying the purple file starts at track 0, sector 2, and then goes to track 1, sector 0. So the file starts here, and it goes in purple, and it runs along here, and now the next leg, or the next piece of that file, doesn't have to appear right after it, it appears over here. So now what we have, so here was the other question. How would you, as you're reading this file, and we're now using linked files, not contiguous files, how would we know where the next piece of the file is? If we wanted to go gather, we want to go out to the disk drive and gather up the files in order, but we want to use better efficient use of the disk space, but we're willing to pay an extra price of taking a little bit longer. How would we know where the next piece is? There's really two ways to do it, but two main ways to do it. But what's a way to say, like, piece 1's over here, and part 2's over here, and part 3's over here?
A pointer to the address.
And where would you put the pointers? And I guess that's really where I'm saying there's two different answers. Would you gather all the pointers together and put them in one spot? Or at the end of each link, would you say, here's the pointer to the next spot?
Probably at
And what's that?
the end of each link.
Yeah, I guess there's a small trade-off between the two, but the way this picture is, it's at the end of the link. So we would go to the index to find the beginning of the file. It begins here, and then we'd start reading the data of the file. And then at the very end, we want to say, where is the pointer to the next part? And the pointer to the next part goes here. And then let's say we're reading the file, and the file ends right about here. And then since we decided to have sectors be dedicated to files, really this part, which is like lighter purple, this is just wasted space, right? Because we don't want to start a new file here, because then if you wanted to find the beginning of it, you'd have to go to like track 1, sector 0, and then a number of bytes into the disk to know exactly where to start. So this ends up being some wasted space. And then the orange file starts at track 1, sector 3. Track 1, sector 3. So here's where it would start. The orange file goes along here, and then this is supposed to be light orange to show that it's not wasted space, the pointer is needed, but it's not part of the file. It's space we're taking up on the disk. And then it tells us the next part is track 0, sector 1. And then we start reading more of the file along here. And then there's a pointer, we have to waste some space that's not really part of the file to tell us that the next part is over here. And then we read along here, and then we have a pointer to the next part, which is here. And then we start reading through the file, and then some random amount of that sector is wasted space. So everything that's in the quote-unquote lighter colors, this lighter color and the lighter purple, is really space we're willing to, space on the disk we're willing to give up just to be able to have the file managed this way. So now, if your operating system is running code that says, okay, now open this file, this orange file, and it's currently out on disk, that's going to take some time. So you have a program that's running that says, open the orange file for reading in read mode or in write mode. And have you ever done that in Java, in your Java class? In your Java code, right? Opening a file to read or write from? No?
Yeah.
What, your input always came from like the I/O stream?
No, I used the file.
Yeah, we
Okay, and have you ever opened files in read-only mode or read and write mode?
Oh, yeah.
We usually have
data to a notepad.
Okay, so but you've done it both ways. But there's kind of a reason for it. If you're opening a file in read mode, you're asking for a lot less work from the disk drive. You're just reading a copy into memory. If you want to open it in read and write mode, you might be writing back to it, which means you'll be altering all these, so you're asking a lot more work to come from the operating system. So that's why they have you open it in read mode or read and write mode. It just means more work that the operating system has to be prepared for. And then also in this example, this gray file, I decided to mix in a contiguous file. So we don't have to like say all files are either contiguous or not contiguous. The advantage to the having the link to the next sector be at the end of the file is that we can mix the two types together. But another thing we could have done was we could have had in the index, this is now going to make the index a lot bigger. If a file has 1, 2, 3, 4 sectors, we could have the file name mapped to the 4 sectors in a row. But now what we're doing is we're reading the address of sector 1, then we go and read sector 1, then we come back here, read the address of sector 2, and so on. So again, it's just how much reading and writing you want to do to bring in the file. Okay, so now let me bring this picture back. One advantage to having a bigger, maybe more complicated index to where the file is was if the file is not sequential. Suppose it's a collection of data. Maybe it's like a database, like tables in a database where you're just adding new people to your, let's say you're created a website like Facebook and you're adding new members to it. And you only care about a particular member. If you could find through the index where that one is, you can just go to that sector directly. You don't have to start at the beginning and read your way through to get to the spot you care about. So if the file is not sequential from the user's point of view, then a more complicated index might be much better for reading and writing from the file because you're not trying to read the whole file all at once. So now we start to get a flavor for how we lay out our files on the disk, because there's different options on how to do it. It's going to impact the amount of time it takes to read and write from the file. So we want to have an average time it takes to read a file. So we'll calculate the amount of time to read the file, and we'll just say, well, it's the number of tracks we're going to have to traverse. How many tracks do we have to visit to grab the file? And then a constant that's dependent on the disk drive. How long does it take for the disk drive, the read and write head, to get to where it needs to go and the disk to spin to line up the location? So every time we grab a track, then we have to grab, for every track that we have to grab, we have to take the time to get to that track and for the track to spin around to us. So the time it takes to read all of the tracks necessary to get an entire file read would end up being the number of tracks times the amount of time it takes to access each. I'm sorry, the number of, maybe that should have been broken down into sectors. But sectors or tracks would work out fine. And then the startup time, every time we go and make a request to the disk, that just might not be spinning at the time. Or the read-write head might even be servicing at some other process's disk request. So and then we might end up going into a queue waiting for our request to begin. So we'll capture that all in one variable called S. So it ends up being how much time it takes for the operating system to say, okay, I'm now ready to handle your request, and then how much time it takes to actually handle your request. So an example might be an inexpensive personal computer might have a disk drive where M is 0.3 milliseconds and S is 20 milliseconds. And then, and then you perform a computation like that. So typical, this was probably about 2 years ago, but the typical speed at which disk drives spin at is 3,600 revolutions per minute. And that turns out to be 16.7 milliseconds. would be the amount of time it takes for one rotation, and then chances are you have to rotate on average a half a spin to get to the beginning of the sector you're at. It'll be whatever half that number is. So then the total transfer time to transfer the whole file in would end up being, the transfer time would end up being, let's say a variable b is the number of bytes to be transferred in for the entire file. N is the number of bytes per track. And so this is an example, this is not the sector example, assuming that there are no sectors, it's just everything is on tracks. And the rotation speed, revolutions per second. So the average access time can be expressed as, the time is going to be the amount of the seek time, which was our previous slide, rotational delay, which is how long on average it takes to spin to the spot where it starts, and then the transfer time. The transfer time is reading the blocks into the operating system, which ends up being this. So that would end up being the number of bits being transferred divided by the number of tracks it's on, and then also divided by the speed of your disk drive. So putting that all together, this part, which is here, and then the part from our last slide, which is here, and then 1/2 an average rotation, would be the average time it takes for the entire file to be brought into memory. And like I said last slide, this S, the startup time, could end up being a very large number if we're queued up behind other requests for the same disk drive. Okay, so now as a read-write head, let's say we had one disk drive, a read-write head is going across the drive is spinning and the read-write head is sweeping back and forth. There's different ways that we can handle the requests that are coming in. A pretty basic one that's simple to implement is first come, first serve, so we've seen that before. So basically, the order that the requests come into the file system is the order they get retrieved off the disk. Another one might be, as requests are queuing up, we could have the one with the shortest seek time handle that one first. So that is basically wherever the read-write head is, of all the requests that are being queued up, we'll push the one that's closest to the read-write head to be handled next. So what's the advantage? This is starting to get very similar to what we talked about in class or two earlier. As far as starvation is concerned, what's the advantage to this and what's the disadvantage to that? So as a read-write head is moving across a disk, all the requests that are coming in are getting shuffled. The ones that are closest to the read-write head will get shuffled to the front since we're already there. It would kind of be like, I'm thinking of it like you're in a building and the elevator's going up and down and it keeps going to the floor where the most recent, the person who pressed the button, where the closest one, instead of going up and down the whole building. It keeps handling the person who's right near the elevator. So what's the advantage to that and what's the disadvantage to that? So same thing here. What we're basically saying is requests that are very far away from the read-write head might take they might sit in the queue a long time, almost a starvation situation, and the requests that are right near the read-write head get serviced quickly. So one way to kind of avoid this starvation thing is to have what's sometimes referred to as the scan seek time algorithm. This is where the read-write head moves back and forth. So it moves like, this would kind of like be the analogy with the elevator. The elevator goes up to the top floor and then always goes down to the bottom floor and just picks up the requests on the way that are in the direction that the elevator is moving, or the read-write head is moving in. So the read-write head starts at the outermost track and starts working its way to the innermost track, and then any requests that come along the way that happen to be on its path, it will handle those. Then once it gets all the way to the inside, it starts moving back to the outside and only handles requests that's on its path. The ones that have already passed it get queued up for the next time it sweeps by. So the slight problem with that one is where the requests that as the read-write head is heading towards the inside, requests that are near the inside get picked up before requests that are near the outside. So we can do the same thing with a circular scan. Just basically we have the read-write head go from the outside to the inside, and once it gets to the inside, it automatically moves back to the outside and goes back in again. So that way, everything is, the average wait time between requests is independent of where it is located with location to the disk. And then the last one was the end-step scan. The read-write head sweeps back and forth as in the scan, but all requests that arrive during one sweep in one direction are batched up and reordered for optimal service time for the return sweep. Okay, so again, these algorithms are basically when many requests are coming into the disk drive for files from different processes. And our goal is to give the files back to the computer, back to the processor, as quickly as we can. And we don't want to do it so quickly that we could have some processes starving. So I'd like to somehow keep it divided up evenly. Okay, so disk space allocation, we've kind of talked about some of this, but contiguous allocation is where the files appear, the data on the files appear in a row on the disk drive. Non-contiguous is where we could scatter them. They don't have to be in a row on the disk drive. We can scatter them. The advantage is that we have better control over how much disk space we take. The downside is we have to keep indexes, somehow link these scattered pieces together, and that ends up taking up space on the disk drive. And when we go to get the file, it might take longer to do because you read one sector and then you have to find the location of the next one and then read that one and keep moving the read-write head around. So, for example, if you were to combine the idea of the last slide where the read-write head is going back and forth and handling requests as the track hits where you're reading from, if you have a non-contiguous file and it has 5 different parts, it might take 5 different sweeps for you to get your file. And you'll be mixing into requests from other processes. Okay, so the sector-oriented linked allocation distributed as individual sectors, and the files get linked together. Okay, so yeah, that we kind of talked about, with the picture we had before, and we showed all the different wasted space. Block allocation is where you get a collection of blocks, sometimes called extents, and that ends up showing up in the MBS operating system by IBM. So what we can end up doing is saying it's kind of a hybrid between contiguous and non-contiguous allocation. We could grab a bunch of blocks that are linked together, and then we could grab a different set of blocks somewhere else and link the 2 sets of blocks together, which we're now calling extents. So it's kind of a hybrid of contiguous and non-contiguous. So we get somewhat the advantage that we can, as we go and read the file off of the disk, once we get started, we can, keep doing a contiguous read, which saves time. We're not jumping around. The read-write head is not jumping around. But we're not required that the entire file is contiguous. Okay, and then index block chaining would be a case where we have maybe one big index where all the blocks are, and then they get linked together. So just different ways. I'm sure if you just spent time, you'd probably come up with these mechanisms, and maybe you could come up with a new one that's interesting. But just a way of writing the data of your file on the disk and then somehow being able to keep track of where it is. So when the operating system comes in with a file name, you could look it up in some type of an index. And then find the file. And our goal is to be able to write the file and read the file as quickly as we can, depending on what our application is. Okay, so sequential files. A sequential file is now from the point of view of the user. So it would be like if you wrote a book, your book should be in a certain order. That's not like people being added to a website of yours where you don't really care about the order, all you care about is having all the people. So this is probably the most common. All records are of the same length. We can break them up and scatter them on the disk in the same length. They don't have to be sequential files, so this is kind of like a virtual versus real. Sequential is from the mindset of the person who's created the file. Where you place it on the disk, the operating system can cut it up and scatter it all around, but it has to gather it back together as a sequential file. So these sequential files are usually used in batch processing, and they're easy to store on disk and tape. And then the question is, if people are making changes to it, let's say you were to bring a sequential file off the disk drive into main memory and start making changes to it and have to write it back, you pretty much have to write everything back. All the sections that you've added would be changed. So if you were to, so for example, if we had a file, even if the file was, if it was a sequential file and it was contiguous on storage, suppose we had this, 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 and this, and this. So this is 1, 2, 3, 4, 5 sectors. Suppose we read this into memory and added some data like right around here. Well, that would make this sector so big it would force data into this sector, which would force data into this sector, and force data into this sector. So once we made a change around here, we're going to have to rewrite the entire file on disk if we wanted to keep it contiguous. What we could do is, sometimes what we'll do is does anyone have an idea for how to not have to always rewrite the entire file of a sequential file if we made an update in the middle of it? So, for example, suppose you wrote a book in Microsoft Word, 100 pages long, saved it out on disk, and let's say it was saved out across a bunch of contiguous sectors. And then you made a change to the third page, which pushed all the data in these sectors off somewhere, or off into the next sector. So really every sector had to be rewritten. So right, you're in Word and then you hit save, you made a little change, you hit save. That's going to rewrite everything back to disk. Is there a way that you could think of, if you needed to, where you don't clear up all of these sectors and then find a whole new batch of sectors and rewrite the file? Is there any way to just make the change? And even if the change wasn't to add to the end of the file, it was add somewhere in the middle, but it's a sequential file. So you have to move the sequence all around where you write it on disk. But one thing we could do is we could just record what changed and the location where it changes. So we could keep a log file to capture all the things that have been added to the file and then periodically update them. So we might be able to say like, oh, it's sector 2 location, 25 bytes into it, this piece of data was inserted. And then just save that at the end. Now the operating system has to know when it reads the file in, it reads the entire file in, then reads the log file and makes all the updates to it. And now from the user's point of view in electronic memory, it still looks like that. It still looks like that file. And then once in a while we would take the log and actually rewrite the entire file. So that could save us, using this trick with the log, that could save us a lot of time if somebody loads in a big document in Word and every time they change 2 sentences they keep hitting save, save, save. You're not reallocating space on your disk drive. So just from time to time we could take the log, the instructions in the log, what's changed since it was originally saved out on the disk, and change that. Okay, now the file type of a sequential index file, an index sequential file, that's the case, kind of like what we talked about earlier. We can create an index and just have pointers go to where all the sequential parts of our file is, and this greatly reduces the access time for individual records without giving up the sequential nature of the file. So it's going to take up more space, and every time we go to save the file, there's more time because we'll have to keep updating the index, but we have the sequential nature of the file and we can read and write to the disk quicker. Then we can have multiple indexes, so basically we can have an index for a certain section of our file, and we can do that for many sections of the file, and then have one index for the overall file. So it can have many levels of indexes if we wanted to. It's not, there's no requirement that we have just one index. Direct access files are files, this is basically where the data in the file does not have to, from the user's point of view, does not have to be in a certain order. So it's not an example like where you're writing a book in Word and all your records have to be in a certain order. This could be like a collection of tables. You could have, you know, people's names, addresses, and phone numbers, and you don't really care what order they're on. They're just you keep appending new people to the bottom, and you're just trying to find a specific person. So we could use a direct access storage device, which is going to use indexing, and the indexing is going to, you're going to look into an index and then just find directly what sector you're interested in. Okay. And then how we do the blocks on a file, there's a couple ways we could do this. We could do fixed size blocks. We could do variable size blocks, and then variable size blocks that are spanned and variable size blocks that are unspanned. So the fixed blocks, so in the case of fixed blocks, we would use an integral number of records to be stored on a block. There would be unused space at the end of the block. So in other words, what we could do now by saying blocking is blocking could be, you're dividing your data, your file into blocks that we want to lay out on the disk, and the blocks could be a collection of sectors if we wanted to. So we can have them fixed length, we can have them variable length, and then if we wanted to, we can have them contiguous on our disk or not contiguous. And the trade-off ends up being, you know, how much wasted space is there, and then finding a contiguous block we want to put storage on. And then when we go to access the file, so the access methods, the two most common ones are queued access and basic access. So basic access, maybe I should have put that one first. So basic access is when you cannot anticipate where the sectors on the file are. So you just read one and then that one tells you where the next one is, and that can be in a random location. If we do have a way of anticipating the order of which the sectors are on, we can put those sectors in a queue. And so if a file had 10 sectors that needed to be read, and the first one and the seventh one are near each other, we could read the first and the seventh at this, you know, approximately the same time and put them in a buffer. So we're reading off of the disk much quicker, and then we're copying that over to electronic memory, and then we can organize the files much better that way. And then another concept, this is just the last thing to talk about, we could, if it really mattered how we, the speed at which we're getting files off our disk, we could actually take the parts of our file and scatter them across different disks. So that way, if we went out to the disk drive system, we could say, I need this file to come in. Our index for the file as well, part of it is on disk 1, track something, sector something. Part of it is on disk 2, part of it is on disk 3, and have the 3 rewrite heads read very quickly. Read all 3 into electronic memory and then construct the file in electronic memory much faster. So this would not be like reading off of one disk and then spinning the disk and moving the read-write head to another part and then reading there and then another part. All the reading is done in parallel. The data is transferred into electronic memory and the file can be put together much quicker. So this is pretty popular for high-speed access of files off of a disk, or off of a disk system. And it's typically called RAID, so it's redundant array of inexpensive disks. Okay, so yeah, so the overall theme is that how we organize our files on the disk, we have options on how to do that. And how we organize them could make it much harder for us to write the file, but much easier to read the file, or it could make it much easier for us to make updates to the file, but that'll take time on reading it, depending on how many indexes, how we link the files together. So some operating systems, the bigger ones like IBM's MBS system, when you go and create a file, it's gonna ask you a lot of questions. Do you want fixed blocks? Do you want variable blocks? How many extents do you want? There's a whole bunch of questions you have to answer. And the more common operating systems we use, like Linux and Windows, don't ask. You just create the file and it creates it. So it'd be interesting to, when we talk about those operating systems, what are they doing? Which one of these patterns are they doing when you go to create a file?